Welcome, everyone. I'm very excited for our speaker today for many reasons. One, his topic. Two, he's been working with me here at UCI for the past 2 months. Short period of time, but he's got a lot done. So Yunfei Zhang from University of Munich. He's a PhD student there, working in Klaus Bogenberger's group, working on traffic and mobility on demand. Klaus has an enormous group of researchers working for him. Yunfei kind of splits the difference between the two, or works between these two topic areas. So please join me in welcoming him. Yeah.
Thank you very much for the introduction. And before I forget, I just want to say, of course, my appreciation to Dr. Highland for hosting me and all the advice and all the nice discussion we had. And also I enjoy, it's 2 months period. It's not like a long time, but I really appreciate all your talks and nice atmosphere here. So my name is Yunfei. I'm currently a 5th year PhD student from the Technical University of Munich. And today I'm pleased to present my PhD topic, which is autonomous vehicles as sensors, which I will use a lot of abbreviation AVaS in their slides. And I focus on the traffic state estimation with the intersection of the operation of mobility on demand services. So before I start, I also want to shortly introduce myself. Who am I? I have a background in civil engineering for my bachelor from Zhang University in Shanghai in China, which is same to Jared here, which I definitely didn't know before I came to UCI. And then I worked 1 year as a cost engineer in a construction company, and I continued my master in transportation systems at TU Munich in Germany, and joined my PhD probably at the worst time, which is COVID time. So I did my first half-year PhD entirely at home office, which is a little bit crazy. It took me like 4 months to meet all the colleagues. Anyway, at the same time, so in Germany, we work as a research assistant as full-time job. And sometimes we always joke that we work like full-time and work overtime for our PhD topic, which I guess is kind of similar to US. And so my current plan is trying to graduate next year. So let's say, hope all timelines will end at 2026. And what I have done so far, or like in the past few years, is I work a lot with different data sources, especially for the floating car data. And for that, used to estimate the traffic and with a form of macroscopic fundamental diagram, and work a lot on the clustering algorithm. So basically, I focus on the, let's say, very typical traffic engineering problem with data-based methods. And besides what I have academically, I also want to shortly introduce myself. As you can also see from the abstract, I'm very active in different sports. I love sports. Unfortunately, I hardly find photos with me on the bike, even though that's my #1 sports. So I can only attach a photo of my bike here, but I'm very enthusiastic about cycling. I'm training for fencing tournament, play tennis, do some cross training, and skiing, of course, which I know Vicky is definitely a big pro. So another question, why I'm here for my research stay is, first of all, I work a lot on the mobility on demand services. And of course, the leading companies, Uber, Lyft, is basically very popular in the US. Also, you can see on Australian companies like Waymo. And also my supervisor, Professor Bogenberger, and my mentor, Dr. Florian Denda have close collaboration with Dr. Highland before. The topic is very close. And of course, the most important reason is I really want to enjoy their kind of California vibes here. And to be honest, I'm entirely a public transit guy before. I also want to experience a little bit driving culture. So
you have to tell them how you got here when you arrived on the plane.
that's true, yeah. So I arrived at Los Angeles International Airport at the first day, and I saw they're taking an Uber to the place I will stay. The Airbnb will take $150. I was like, okay, I'm not gonna pay that. Let me try the public transit here. And it took me 4 hours from the airport to the place I stay. So basically take an express bus from the airport to the Union Station in Los Angeles, take their Amtrak, take their intercity railway from Union Station in Los Angeles to Anaheim, which I experienced the mobility center there. And I took a bus for 1 hour driving, which basically ran all the hours around the Main Street. But it's cool. I experienced all the public transit. Yeah, but I definitely like drive afterwards, and that was pretty amazing. Yeah. So that's everything about me and the reason why I'm here today to present my topic. But before even going to their contents, I want to say, because I know all of us have different backgrounds in transportation. So I want to first present an overview of what I'm doing and what is background of the PhD topic, and then maybe go a little bit deeper into details, especially on the modules I'm doing right now at UCL. So again, starting with my background and motivation, and then I will talk about the methodologies I have used and currently developing, and probably also the finished works in the past. And then I will dive into the focus of my research stage, which is the predictive routing modules. And finally, with a short summary of everything. So background and motivation. What is the background of the research areas I'm studying? And also based on this current situation, what motivates me to focus on this specific topic, which is traffic state estimation plus mobility on demand services. I guess all of us can agree that autonomous driving or autonomous vehicles will be the future. It's kind of interesting because just half hour before I was at this MIT forum, and they invited their scientists from Waymo, and they're talking about, okay, why we expect that to be like on the road a shorter time, but why it's still like at the test phase. And of course, there will be a lot of reasons, not only on the technical parts, but also in the legal parts, under ethical parts. But I think what we can all agree is the autonomous driving will slowly replace the human drivers. And even though it's like a long period. So my motivation starts from, okay, autonomous vehicles are equipped with these different sensors. They have cameras, they have LiDARs, they have radars, and they use these sensors to collect data for self-driving functions. But what other functions can I use, or what other application can I use for from this data? So that's the whole idea is from. I'm not doing with anything with autonomous driving, but I'm using their data which supports autonomous driving. And this comes to the point of the mobility on-demand services. So imagine, right now you are running Uber as an operator. So probably what right now this current situation is, you need to spend a lot of money to their different map providers for your routing algorithm. So as far as I know, their current Uber app for drivers, they have their routing, which is based on the Google Maps. And what I thought could be interesting is if I am the operator of Uber and I have a fleet of autonomous vehicles, maybe I can use the data collected from my own fleet and like send back to me and use that for routing. So that is the basic idea of the my PhD topic. But of course, there will be some extensions. So imagine we also have the traffic sectors, like control centers in the market. So maybe they will have some kind of data, which is like typical loop detector data or cameras installed in the intersections. And we, as the operator, Uber can use this external data using their data fusion technologies for my routing. And maybe at this point, you will have the question, okay, why would the traffic control center share the data with me, right, as a private operator? And that goes to the other loop, which is from the other side, as me, like running Uber, I can also provide my data. So the data collected from my own vehicles or from the Uber drivers, or in the future, autonomous vehicles, to the traffic control center. So this creates this data exchange loop. And I call it in different cases of the application. And why does it work? I will call it a win-win-win situation, or hopefully a win-win situation in ideal case. So imagine what I'm doing is I have this AVaS sensors informed predictive routing algorithm, and we have different stakeholders in the market, which is me, of course, operators, but we also have the passengers and traffic control centers on the side. So these routing algorithms can hopefully provide more data for the operators. And this routing algorithm should save or reduce the travel time for the passengers if it works, right? Otherwise, the routing doesn't make any sense. And passengers in return, because this mode will be more attractive, they will create higher revenues back to the operators. At the same time, we will have this data exchange between the private mobility on-demand service operators and the traffic control center. And also, traffic control centers can provide some regulations benefits. For example, or not even benefits, in certain areas, I only allow you to run the mobility on-demand services if you agree to share the data with me. Of course, anonymize the data. So hopefully there will be a win-win-win situation for all the players in the market. But however, for my PhD topic, I only focus on the loop between the routing and the operators part. So if you have any ideas regarding how the different stakeholders interact in these loops, I will be happy to discuss, but that won't be my focus of my PhD topic, but it could be 3 entirely different seasons. Yeah, so based on this background and the focus, I have the working title of my PhD topic, which is, again, autonomous vehicles as sensors. And I only use that for estimated traffic. And this estimating traffic is from purely the operators of mobility on-demand service. Okay, so now I have the topic I want to study. The first thing is that technically feasible? Is that enough data or like the accuracy or the frequency, the availability supports me to do a research like that? So before I talking about the feasibility, I want to give you an overview of the status quo, which is what we have right now. So basically in the past, I would say like 50 years, everyone use floating car data, which is you have a car running in the network, and for every time step, you will have the ID of your car, the running speed, and the geographically coordinates of your car. So you basically knows for your own car, what is the status of this car, what is the travel speed of the link your vehicle is running on. But in the past few years, what we have is called extended, so XFCD data. So basically, what the extended FCB is doing is instead of just reporting the ego speed and their geographic locations, the vehicle can detect the surrounding traffic. So instead of return the speed and the location of one vehicle, it reports this ego vehicle plus all the vehicles in their detection area with all the sensors, and which is pretty much, I would say most like modern cars will be equipped with. And this is the question. Yes.
Oh, sorry, I was just gonna ask what the symbols were, but it looks like you're gonna explain.
Uh,
The gray symbols, like,
you mean like these triangles? Or
it's like in the shoulder of the road.
the bicycles? Sure. Yeah, sorry, I will explain. So basically, this like is urban settings, maybe European ones, because you have more cyclists and pedestrians. So for this rightmost lane is pedestrian, and this is cyclist. And we have their vehicles with this Wi-Fi icon, means it is connected, and so of course equipped with sensors and then connected to the central control. And you have the black vehicles without a symbol, means they're just normal cars not connected to their operators. And this is the current state. And what we picture as perfect for traffic engineer is we have so-called full connectivities. So we have everything to everything connection. That means not only all the vehicles right now are connected, but also we have pedestrians, cyclists are also connected. And this could be done by the wearable communication device or even sensors. So in that case, probably we don't need signals anymore. So the traffic control centers will just tell the vehicle when to start and when to stop. And we don't have to guess whether this cyclist will go straight or turn right or turn left if they don't have a hand signal, because this can be communicated with their wearable devices as well. So maybe they have a navigation device like a watch, tell them where to go, and this information will be sent to the center control of the intersection. So the car knows they will turn left, they will stop right before their stop line. So that is ideal case for the traffic engineers, because we know where every road users are going. And what I want to solve is something in between, because this could be, it looks like 30 or 40 years, or let's say ideally 20 years later. So what I want to try to do is something between the current state and this ideal future state, what I call as AVaS sensors. So basically, instead of just human-driven cars equipped with sensors, I have this picture of AV driving while mixed with the human-driven cars, represent as the black cars. So this autonomous vehicle will be equipped with different sensors and have this detection zones covering certain range of the road. So the idea is within this range, these autonomous vehicles can detect every other road user, no matter they are cars, they are pedestrians, they are cyclists. So I'm focusing on this mixed, so with us mixed traffic conditions with both autonomous vehicles and also human-driven cars. And so this is the technical feasibilities. So I just want to show you that it's not something we already have, and that's why I need to use simulation to study the feasibilities, but it's also not like something like super fancy for the future, which you have the ideal case. It targets or aims for the near future, which we have some autonomous vehicles running, but not entirely. So as long as in this technical feasibilities, I want to show how it looks like from the operator's perspective, which is so here is like map for Munich, which is the city I live and the walkways, and of course you have as an operators, you should have a network which have different traffic states. And right now it's represented by the Google Maps color, but hopefully in the futures can be collected from the operators' own fleet. So the operators have different vehicles running in different parts of their network. And the first scenario is what we call, in use case, what we call the moving observers. So you can just think of as like extended floating car data. You have these autonomous vehicles running and they collect data constantly around the path. But the second use case is what we call parked observers. So imagine you have fleet, maybe due to their off-peak hour, some vehicles are not like running or carrying passengers. So they are just parked like around the roadside. And what I thought could be used for is these parked vehicles can turn their sensors on and collect the traffic states like passing them. So just serving as like a loop detector data. But instead of loop detector, you can park vehicles anywhere you want. So it's kind of like moving parked observer. And finally, the final use case is imagine we don't have the traffic states at certain part of the network, and you have some idle vehicles. You can even assign these vehicles to the areas you want to collect data. While this part can be tricky because you can also think, okay, why do I need to do that? Because if I send vehicles to there, they will cost extra mileage. But if you combine them with the gains you will get from the traffic informations and also rebalancing for the future demand focus, it could be beneficial. So that's will be the three use case of this AVaS sensors traffic state estimation pipeline. And okay, so now I talk about the perfect imagination I have. I did some research on the current technical situations. I imagine how what works for the operators, how it works for their different stakeholders, but does it really make sense, or it's just my research fantasy? So I actually have a chance to talk with a few people working for the municipalities. So one person, ITS chief advisor, he's working for the city of Helsinki in Finland. He told me that actually in Helsinki, they have a fleet of 50 vehicles to detect the road conditions. What they do is they basically have a LiDAR sensor, and if they find some uneven places on the pavements, they can directly report instead of people inspecting, or you receive a report from the citizens. So he's quite interested in the idea of, because they already have the fleet. So maybe not only use the fleet for the infrastructure maintenance, but also for traffic control. And the second interesting feedback I recovered is from one person working in Belgium. So what he told me is a lot of small cities in Belgium or other like European cities, they don't have so much budget for maintaining their traffic detectors like loop detectors or cameras. So what they thought could be interesting is if they have ideas, so allow the MOD operators to collect data and provide the data for them, they don't have to install or maintain these fixed locations detectors. So there will be a very much big saving for the municipalities as well.
So Yunfei, yeah, this is a very interesting question.
Yeah.
So you mentioned about LiDAR sensor for the first case. I mean, but I suppose these are still human-driven vehicles.
Yes,
is that right?
absolutely.
So I mean, what would be the unique advantage of autonomous vehicle in this situation?
So easily speaking, saving cost, because you had to
Okay.
hire people, human drivers at the current moment. I mean, it sounds like cruel, but it's definitely true. The reason why we are doing like autonomous mobility on demand services is because it was saving driver costs.
Okay. So actually, I think related to the second one, But now I feel it's not lack of data. It's just, because we are using GPS devices and a lot of people using it, like Google, like Apple, they have a lot of data. Just how to get the data to be shared among different stakeholders might be the challenge.
Absolutely. And the data format order, yeah, so I think it's a very solid point. It just like, I suppose the perfect situation is they will have this kind of exchange plan, which I do not study, but I definitely think it will be a real challenger. Yeah, I guess like from my point of view, not my PhD thesis research is there are municipalities, especially when you have like European unions, you have a big institute to regulate their data format for different countries. You can have like a regulated standard format for data sharing.
Yeah, probably privacy concern.
Absolutely,
there as
and
well.
it's the top one issues for European unions for sure is data privacy. And then again, like I said before, you can regulate these services. For example, Germany banned Uber for several years because Uber didn't pay the minimum insurance for the drivers in Germany. So like you can ban a service if they don't like follow in this data exchange format. Of course, it's like a little bit let's say more hard regulations from government, but I guess it's
So I don't know if we are going together. It looks like those are strong arguments to support to deploy AV-based
absolutely. Yeah.
floating cars.
I'll be definitely interested in following this up, but after my PhD thesis. But that's really cool. Thanks for them. Yeah. So I get the feedback from the people from municipalities. And the last slide, I just want to shortly summarize the background and motivation. So I start from the simple idea of for the autonomous vehicles, they need sensors to support the autonomous driving function. So can I actually use the data from the sensors for traffic state estimation and prediction? Then it comes to play of the autonomous mobility on demand services operators. So it makes sense because they can save money. And this formalizes my primary motivation, but also together with other stakeholders, this can be beneficial as well. And all this formalize my topic, which is AVaS sensors in operation of mobility on demand services with two modules. I will mainly start it, which is first the traffic state estimation prediction, and second is AVaS sensors inform the routing. And this have two scenarios, which is moving and parked observers. And finally, I got some approval from the municipalities. Following these two modules, I have two main primary research questions. First one is how accurate can this traffic state estimation and prediction module from AVaS sensors be compared to their other data sources, which we have right now, like loop detectors, cameras, or just GPS trajectories. And second is related to the routing algorithm. So how much travel time can be saved by this predictive routing algorithms based on the traffic estimation I get from the first module. So based on these two research questions, I will then present what methodologies I have been currently developing and have used so far, and also which modules have been already implemented in the methodology. So again, like I said before, since we don't have really level 5 autonomous driving vehicles, autonomous vehicles on the road. So in my study, I was focusing in the simulation to illustrate. That means I not only need to simulate how vehicles take different routes in the network, but I also need to simulate how vehicle collect data. Imagine, suppose they are already level 5 autonomous driving. That's why first I collect the detection attributes, and then I use this technical attributes of different detectors to simulate the data collection process in the simulation. So actually in the simulation, we know like which vehicle are at where or what is the speed or densities, but I pretend that I don't know in the simulation, and I have a module to simulate my ego vehicle can collect only the informations in my detection range, but not like the whole picture. So that's why this simulating the data collection will be the first module. And based on this simulated AV collected data, I will use that plus the external data source. So for the external data source, I can just easily put loop detectors in the simulation and use the data from this simulated loop detectors. And the results of this module is I will have the estimation and prediction of the traffic states for the current state and for their next few periods. And I use that for my predictive routing algorithms together with the other operation modules of autonomous mobility on demand services. I simulate the vehicle movements. And of course, this will be a loop because whenever your vehicles move in the networks, you will constantly collect the data. And this data will further enhance your traffic state estimation and your prediction. So it's kind of interactive process. I saw several hands, maybe. Yeah.
What's the difference between traffic state estimation predictions versus real-time future traffic states?
So basically, traffic state estimation estimate the real-time states, and the prediction predict the future states. So this is okay. So the rectangle is the method, and this like diamond shape is the data. So this module produces the data, but it's the same thing.
Oh, so we can use the external data for traffic state estimations, right? Or you're gonna combine these two data sources to predict the traffic state without it.
Yeah, so there will be like a few different cases. The first case is I only use the external data as the baseline, which is what we do current right now. And then I use only the AV collected data to compare with the baseline. And then I combine them together using the data fusion to see whether after data fusion, like they will be better than a single data source. And hopefully, yes. Right.
Yeah, so I was just wondering, so I assume this is, like you're taking up the perspective from an operator, right? Like, would not be able to access other data like Google and so on? Because otherwise, like, what would be the fundamental difference from getting this data from Google, right? Because all the cars are connected, and this data will be easily available, right? So you're assuming that this company can only have access to their own data?
Yeah, because so as far as we understand is, even for Uber, this kind of the motivation is you had to pay money to using the Google Maps services for your routing algorithm. So you have the data, but you need to pay for it. And what I want to propose is, instead of paying Google Maps, you can use your own vehicles.
Yeah. I just concerned, I don't know like how big this split should be relatively to the proportion, like to the dimensions of this.
That's exactly what I want to try to find in their case study for different penetration rates, how they perform. But I will introduce the next few slides. We see that at certain penetration rates, you can really recover a nice traffic estimation. And also like just for the information, so for example, the Google Maps, what we know is it uses trajectories, right? So if a vehicle is stuck or like 100 vehicles is stuck in a certain road sections, Google will turn the road section into red. and it's congested. That sounds very solid, especially when Google has so many users. But you can also easily like manipulate the Google's. So I'm not sure whether you see this famous meme that one person just drag a trolley with 200 cell phones, and then the Google just labeled the road section as red, and this person can just travel alone like with free speed because everyone else will be rerouted, right? So what I'm trying to say, like instead of using Google's the trajectories, AV, they can literally see the traffic. They can see whether there's a queue instead of their intersection. They can see whether their road is clear. And even with a municipality point of view, they can see their like other road users, their cyclists, the pedestrians. It's kind of their motivation why doing that instead.
Can I say something?
Yeah, of
About the data, what is the range that you are considering for the, these sensors? Because, there is different sensors and, I think about that queuing thing that you mentioned.
Yeah.
What if, some special cases, that there is a single color, thing right in front of the sensor?
Yeah.
That sensors, I would say, cannot detect any queue absolutely in front. So, yeah, about those questions, yeah.
So first question, it's like I can't give you a number because different sensors, we actually model that in the papers as well. Is we have different sensors, we have cameras, and we have a certain angle. How to call it like this? Like it's like a radius, and with a certain angle, you can see like you have cameras mounted in the front, you can see on the side. You can have a cameras mounted on the side door as well. And you also have the LiDAR, you have the radar. So we actually taking the leading detectors attributes for different types of detectors in the module. And regarding the second question, that's exactly what we model in the computer vision scenario is we consider the case. If you have a big vehicles in front of you, like 2 meters, then everything will be blocked. It's already in our simulation. And what we're trying to find out is even with this kind of like finding from the front vehicles, you can still see something. But I will show in the next few slides how we actually do it. Yes.
Do we have anything to check the data quality we are receiving from AV? Because what if there's a cyber attack and the data, the AV sensors they're providing might not be correct or real?
I think yes, we do, but that's the topic of my course. Unfortunately, I can't answer like about that. I assume a perfect data exchange frame, and I assume the data is there. I just use the data for my own purpose. But that's a good point. And that's definitely the major focus we should look at when we actually want to have this kind of exchange scheme. Yeah, so this is the whole flowchart of my methodology. What we have done is first we write this concept as a paper, and then we have the second paper focusing on to your questions, how to collect data, how to simulate data collection process, considering different attributes of different sensors. And then we have the third papers regarding the traffic state estimations using the simulated data for traffic states estimation within a German city network. And the fourth one, which is currently what I'm working with at here for their predicted routing paths. So for the first papers we have done is we basically illustrate that using rather low penetration rates, we have 2.5% moving and plus 2.5% parked observers. We can already have a good fit of their MFD for the class from the cluster level. And so the whole purpose of that paper is to say, okay, we have an idea and it might work for network or cluster level. And
so if I can go back to this figure. So is this for one road or for one network?
It's for the cluster.
So for the network.
The whole network, right?
Yeah.
For the whole network, then the density many times should be measured by vehicle per km mile, or I mean km lanes. I mean, you should consider the number of lanes as well, right? I mean, or in the
Yeah,
US, we can call it vehicle per lane mile.
True, yeah, we actually did that, but I should label that in the legend.
Km lane.
Yeah, that's the per lanes density.
So how big is the network? Is Munich the metropolitan network?
No, it's calibrate so I think it's a district of a German city called Ingolstadt, which Audi is located at headquarters. But it's a small. So first of all, the whole Ingolstadt is a small city compared to Munich, and then we only focus on the district. But the whole network is well calibrated with the traffic demand and the signals from all of our previous research projects. That's why we use that for our simulation.
Is this assuming that the vehicle distribution between lanes is relatively homogeneous? Like you don't have one lane that's mainly freight vehicles, one lane that's mainly passenger vehicles, something?
Yeah, because it's a small district. But of course, like that's exactly the downside of MFD, because you can only describe the cluster like zones. You can't say, I mean, you suppose it's homogeneous, but it's never homogeneous, as we all.
I assume the results depend on the algorithm also, the estimation algorithm.
What do you mean by estimation?
So when you have data from the vehicles, then you have to process it using some algorithm to estimate the state, right?
Yeah, so actually I won't call it an algorithm thing for this idea, because what we do is very simple. I walk here, like within this 3 meters, I saw 1, 2, 3, 4, 5 cars, and I know my detection range among different lanes. I have their lengths, the total length of different lanes.
So you don't use any traffic flow model?
No, I just 5 vehicles over the total length. This length calculate a very basic bias density, and we try to illustrate even this basic bias densities can describe a network. So there's no algorithm anymore. It's purely densities vehicle definition.
So the flow, the values is 250 is the maximum values, right? So
yeah,
that's because like normally like the load capacity is about like more than 1,000, right? So in terms of that values,
Yes.
how can you explain that?
So that's the lane capacity, first of all. That's a little bit like, and second, it's urban road. And normally the characteristics for Ingolstadt is it's basically I would say, so only people working for Audi will drive to work and drive from work to home. So the traffic is normally like only peak and zero and peak and zero. So it's not a big city. That's why the flow is slow, not because of the capacity, but because the demand is.
In the European Union too, right? It's compared to California, they drive farther apart and slower too.
That's true. And you have to wait for cyclists and pedestrians.
So that means that this point does not reach to the capacity point.
No.
So the capacity should fall over there, and this only data is kind of like a very starting point of the like a fundamental diagram, right?
That's a cool question. I think like, I mean, from the shape you can see here is kind of the capacity. So I guess, okay, to answer your question, it's basically, since we do the clusters, we have very low, not like high speed, high road classes roads, but you also have the residential roads, and this drop the average capacity.
Yeah, it's not a highway, right?
I mean, the road capacity in the EU is lower than the US and
Road capacity.
because of the driving characteristics, the speed limit and the spacing. The Customer kit.
Or is more on the, the green ratio. I mean, how much green time is allocated to cars, because you have to share with pedestrians, with cyclists, and so on. So is a speed limit like a 40, 50 kilometer per hour? That's it.
I tried to do math of 4 miles, 2 kilometers. I think like, okay, that's one thing I found crazy in US is like you can try like 45 exceptional crazy, okay? Okay, I found crazy in Alabama, like you can drive 45 miles in the city, but like I think in Munich the highest I can drive in the city is 25. Yeah, it's
25 kilometer or mile?
miles.
Okay, yeah.
And you still have like, especially in the city center, because Munich is such a cyclist city.
Yeah.
And they even give like, so one of my commuter route, they used to have 2 lanes for the car, and they recently just divide the 1 lane entirely for cyclists. And what I can also say is, if you look at the traffic average speed in German cities, so I believe like in Munich, the average speed for cyclists is 18 kilometers per hour. And the car driving is 19 or something. So basically you cycle and you drive is the same average door to door.
That's like walking in Manhattan, the same, walking and driving.
But also, like when you drive in Europe, if you drive the same car spacing as you do here, people get really mad at you. Like they think you're driving too close to them.
Yeah, but we can talk about the MFD or capacity topics for sure later. I think it's a lot of interesting things happen, and I still have to like, I have to remember by myself like which part of the network we have used. Yeah, but the idea is we have a concept, we try to illustrate this correct. And the second paper, we focused on the simulated the data collection. And actually, so Dr. Highland reminds me that the results actually looks super bad. Is we only use the distance-based detection. So we don't, to answer the question, we don't use a lot of sets of traffic sensors. And it's pretty biased from what you can see from the data. And we don't have the parked observers, which means all our vehicles are driving the net. And that creates a lot of bias, because imagine during the off-peak time, you have one vehicle driving in this lane, which is the ego vehicle. And you will always count yourself into the calculation of traffic densities. But maybe like in there 10 links surrounding you, there's no single car driving because it's off peak. But you will always like overestimated the densities because you count yourself, right? So that's kind of the bias we get. And so the results are not so satisfactory. That's why in the third papers, we include this computer vision algorithms. So we, in the Zumo simulations, we introduce computer vision. First, we reconstruct the 3D point of view of the simulations. We model the cars not from a 2D object, from 3D with height. And then we can see, or we can't see certain vehicles because they were blocked from the side. And then we train a neural network for detecting the vehicles and actually return which vehicles can be detected. So from the figure, what you can see is if we have an ego vehicle, all this, actually I don't know color, is that green or? Color blindness. So these vehicles can be detected, but if it's behind our vehicles, you can see them. And if it's like outside of the detect zone, you can see them as well. Or if it's blocked by a building, you can see them as well.
So, yeah, I think that's can you go back to the earlier figure? mean, that's not biased. I see a substantial systematic errors there, even like the free flow speed is not correct on the top left.
That's
and,
true, yeah.
Well, what is going on here? I mean, the speeds are substantially different from. I thought speed would be the easiest one to estimate or by floating costs, you know? If there is some-
Yeah, so we some of what the errors can be from. So first of all, like I said, before we have the we have only the moving vehicles. Second, we have a rather low penetration rate. And third ones is this space physical calculation of densities and speed might not be correct. And that's why in the following papers, we're trying to use the estimation model, so the algorithms instead of this calculation. Yeah, but if you ask me what is wrong here, especially the speed.
Right, the slope is
Yeah, I know.
so different. I mean, the speed I thought, with floating car, it would be rather easy to estimate the average speed, but now turns out that is a little surprise. What kind of simulator did you use?
Zumo.
Yeah.
Yeah, but I admit that's definitely like certain systematic like errors existing. Yeah. So to tackle that problem, that's what we done by the computer vision method, which we, of course, you can still see the point estimation is pretty bad because we only calculate the single. So we calculate this data from vehicle point of view. So we have 10 vehicles, so we calculate about all this as observation from these 10 vehicles. But then we, instead of calculating from the vehicle point of view, we switch to the link point of view. So instead of just use the data from the vehicle, we estimated the data for the link. Instead of saying my vehicle is running here exactly at a speed of how many and what is the densities, I calculate the links based on how many vehicles have been on this link in the past few time periods, and I use that to calculate my link level densities.
I kind of get it. I mean, that's what you said about 19 kilometers per hour. That is end-to-end speed.
Yeah.
But using loop detector, we are really detecting the moving speed.
That's true.
I think that probably is the reason why they are so different.
Yeah.
Hey,
Yunfei, I don't know if you can hear me. This is Andre.
Hey, hello.
we can hear you.
We can, yeah.
Okay, good. So I've got a question. I hope it's not too deep into the weeds, but how do you actually measure density from your autonomous vehicle simulation? Go ahead.
So we have like two ways. So the first way, which we did in the last paper, is we calculate what is the total length of my detection zones. And we have the vehicles within our detection zones, which is calculate density by the number of vehicles we detect over the total length. So that's the first one.
And this is as a moving observer, right? Because these vehicles are floating in traffic.
Yeah.
And do you account for the fact that because you're moving in traffic, that you're going to observe less vehicles than you would as a stationary observer in your density calculation?
That's correct. Yeah, because you have to pass your own vehicles to the calculation.
Well, if you're moving in traffic and let's say it's uniform speed, right? Then you won't be observing any vehicles passing you. So technically, you might, if you use that as an observation, then you might think that, hey, density is 0, but it's really not true because that's because you're just floating with traffic. and all the vehicles are equally spaced from you, maybe just beyond your detection zone. Is that accounted for in this calculation?
That's not accounted for the calculation in this research, but that's what we're trying to do in the current paper.
So could that be the reason for the systematic bias here, you think? Because it seems like your density, I mean, that's,
Yeah.
you know, there's a systematic offset that, you know, Wen Long was mentioned, brought about earlier.
Yeah, we haven't thought of from this perspective, but I think it's a good point, and we should definitely include that. And what I also think could make sense is I agree that this bias will be always there as long as you have the vehicles moving. That's why we will change the methods of estimating the traffic densities in the current method, so we do not observe or like calculate the densities, but we're trying to see the queue and estimate the queue length instead of estimating the density itself. So because we believe this method is not reliable, even though we try to fix it, so we just switch another way to estimate traffic. Does that make sense?
Yeah, I guess, or maybe there are different ways to estimate density with a moving object. You know, yeah, I'm just thinking out loud that maybe if you have an autonomous vehicle,
yeah,
you can literally observe the surrounding vehicles and estimate the microscopic, you know, spacing between you and the vehicles to have that point estimate of density just around you instead of trying to observe flow or, you know, and derive density from that, right?
Yeah, that's correct, and that's what yeah.
And yeah, so anyway, thanks.
I think methodologically, I don't know if you guys use Edie's formula. I feel that it's how to use Edie's formula, how to define the domain actually could be important here. Yeah.
Actually, every paper suggests how to calculate the density based on the moving observers.
Yeah, we do. We saw the paper. Yeah, just like but like for example, at this method, it's still using, if I remember correctly, so the passing vehicles, etc. But for us, the data format is a little bit different. So we not only observe. So imagine we are following a peloton, then we can see all these vehicles will be constantly there, right? So it's not like we pass them or they pass us. So we can not directly using that because the data is kind of different.
Yes, maybe a related question. Did you check the sensitivity of your results to the sensing range?
We did. Yeah, I didn't show the figures, but we did test. So for the computer vision, it's kind of based on how we simulated the computer vision. But for the other sensors, we calculate different range, and it shows no big difference in the arrows. That's the problem. So the results is different for sure, but the arrows are kind of similar.
Both patterns are pretty clear, I would say.
Yeah.
Right? I mean,
so we believe that is a dead end. So we are switching to another method to estimate. Because if we consider the application of routing, for routing, you don't necessarily need the density. So you just need to know how much time it takes from A to B.
Well, you might be onto something. I see this both sounds reasonable. Actually, I mean, this one is from the loop detector data. We generally observe this kind of shape. But if you look at the end-to-end travel,
yeah,
this also makes sense as well.
Yeah, so for the routing, I mean, so like I would say like densities of flows are more for, or speed is more for the traffic control perspective and the travel time at certain links, or like the total travel times of certain links, which is your route. It's more from the operation. But I appreciate all the comments, and yeah, also we consider this point and we're trying to switch to another way to estimate the traffic states. So yeah, that is the results from the traffic state estimation, still like a lot of bias. That's why what I'm doing here in the past 2 months and current state in the next week is I'm trying to refine the traffic state estimation prediction module plus the predictor routing. And I will go a little bit deeper into the topic, but I'm not sure how much time we do have, because it's already over 11, right?
Yeah, you have about 10 minutes, would that be okay?
I can do 10 minutes, yeah. So the idea is, so what is the predictor routing? What I'm trying to do is, imagine we have like a network like that, very simplified. And with the current routing algorithms, what we will also see from Google is we know the traffic states for the current state for different links. So I start with time t0. And apparently at the time t0, the fastest route from A to B is go from the upper, because it's 5 plus 10 minutes, the shorter one among the 2 options, right? And the problem is maybe after you travel from A to B, so after 10 minutes, you see, okay, instead of 5 minutes on this link, right now it's 15 minutes. So what Google Maps right now will tell you is you have to reroute, right, to a faster link or faster route in this case. So instead of going from B, C, E, you will go to like lower BD.
But to be clear, I mean, Google Maps already predicts right now when it gives you recommendations, right? So probably the scenario that you're talking about is when there's an incident. Is that the way I should understand? Because Google Maps already kind of predicts.
Yeah.
I'm not sure if that's true with Google Maps. No, because I mean, you could type Google Maps in and you're going, and if you're going on a far trip, sometimes it'll update, sometimes it won't, but the traffic is changed.
But I think it updates when there's a deviation, right? There's an incident or something.
I mean, when there's periodic traffic, like regular traffic, say peak hour traffic, it might not update.
Yes,
Right.
exactly.
But the traffic still grows.
Sorry, guys.
Yeah, suppose like congestions.
I have to return papers.
Just pretty sure like the recurrent ones are already captured. So talking about the non-recurrent state. So I mean, it's prediction, but you have the recurrent traffic patterns and you have the non-recurrent incidents, accidents, events, whatever, the not regular ones. So in this case, you'll probably go to the lower one because now it's a farthest route. And the farthest route now is the 10 minutes you have already traversed and the 10 plus 10 in their next 2 steps. Okay, so let's just follow this way from B to D. And in this case, extreme case is, okay, we are already at this node D, but instead of 10 minutes because of accidents or like events, now it's congested. And we know, okay, instead of 10 minutes, now it's 30 minutes. But we can't take the upper route because we are already in the middle of this route. So that makes us actually take a longer route than we originally choose. And now it's 10 plus 10 plus 30, which equals to 15 minutes. And if we look like after trips, we realize, okay, instead of taking this extra 15 minutes route, we can take the upper one, which is definitely shorter. And however, at the beginning, we estimate that the farthest route will be there and will be 25 minutes. And actually we take another route, the resulting longer travel time. So what I'm trying to do for the routing algorithms we are developing is two goals. The first one is find the actual farthest route, which consider what will happen in the future with this accidents or incidents, non-recurrent congestion. And second, return the predicted travel time as closer to the real actual travel time. So what we have thought is instead of using static or like predict the travel times, we'll have a travel time series for routing. So all starts with this travel time for the link L at time t0. Instead of using that as the input for the routing algorithms, we're trying to include this time series with the prediction. And the question is how to do it. And again, I will use different data source. The first one use the external data, loop detector data. And second, use AVaS sensors to update the surrounding regions. So like it depends on how much areas we should consider and how homogeneous different links within these regions could be. And the third one is combine these two together with data fusion. And again, so we switch from density estimation to the travel time estimation for the routing perspective. And for that, we have a few key literatures. What I think could be very relevant, even though they are a little bit old, it's because the travel time or like traffic state estimation prediction is pretty much a very mature topic in the research. So we have a few literature I find, okay, sometimes they use the sparse travel time. So that could work for me because I have rather low penetration rate as well. Sometimes they use the filtering method for the GPS trajectory. I can use the filtering method for estimation prediction, but since my data is different, I'm not following it exactly the same way. And there also another classic paper is they actually use mixed AV data, which is perfect for my case, but they use it for the macroscopic model, so more general. And I'm focusing on both microscopic and macroscopic.
Yeah, and also a question for the three method. I don't know about RNN, but the second one,
yeah,
I believe they have some underlying fundamental diagram.
That's true.
Assumption.
Yeah,
here.
yeah.
Maybe third one as well.
Yeah.
But from your study, it looks like the fundamental diagram shape can be very different depending on the way.
Yeah, yes, that's true. So I'm not sure whether I have time for that, but like what we want to do is we use the fundamental diagrams for the further routing. Maybe I can directly jump to the slides because I think that one is more interesting. So what I'm trying to do is I have different like simulation platform for my routing algorithms. So Zumo for general traffic simulation, FreePy for the simulation of their mobility on-demand services, and this is my own code. So I start with the initialization of code simulation by starting the FreePy first. I have the network, initial link travel time plus zone system, and I have the demand for mobility on-demand services. And so this initiated the simulation of FreePy. So basically, which passengers, which vehicle should carry, follow which route. And I insert this route of these MOD vehicles to Zumo plus other background traffic. This initialize this code simulation. And for the simulation, I have a time step, which I update the traffic states, prediction, and the routing. And every time step, I will divide it into 4 steps. So the first step is the Zumo will drive MOD vehicles plus other vehicles, and also the loop detector data. And the loop detector data can be used to for the link level prediction. And which I get a prediction purely based on this loop detector data plus certain weights. And these weights are calculated based on the different factors, like how many detectors in and how frequent, whether the roads are similar, the road classes are similar. And what I try to do, answer your question, sorry, it takes a little bit longer, is we try to estimate the MFD based on this one, instead of based on our own AVaS sensor set.
Okay.
And so continue for my.
Then for that, I mean, there are, questions related to where we have loop detectors. The shape can be very different as well.
Yeah.
Whether it's mid-block or really close to stop bar, the shape can be very different. Yeah, but what you found, I think both are meaningful, but somehow they should be coherent with each other. You basically show that with different ways of measuring. I think this is consistent with the discussion in the MFD community, where we place loop detector matter a lot.
That's true. Yeah.
And then of course, people even assume green shields from the diagram.
Yeah.
I think that's quite off. Good. Thank you.
Thank you. So if I may continue regarding the time step. So this is the first step purely from the simulation. And the second step is from the Zumo, we apply this 3D vision module, which basically give us the MOD vehicles observations. So like what is surrounding scenarios, with different sensors. And then I use my own method, which calculates the link level prediction corresponding weights, and plus the original zoning system from the network, plus the MFD to update from zone level prediction, and this plus the zone level weights. And zone level weights can be calculated, for example, how heterogeneous of the observations inside of a zone. And all these three will be combined into a weighted prediction for link level. And that's how we think of how to solve all these systematical errors we talked about before, is we trying to use this dynamic self-adaptive weighting system. And if we really have very few vehicles, we'll trust the zone level more, which heavily rely on the historical data. And for this weighted prediction, we put it into the predict routing algorithms and update the routes in the last step of this time period, continue over a different time period. I think that's it. I don't have time for a summary, but.
What do you guys think? Let's give them a little bit of time. Everyone seems to be really engaged.
Okay.
Not
You
surprisingly.
didn't want to go deep on traffic, but they made you go deep on traffic.
We've had a lot of our discussion in the presentation,
Yeah, I
so
suppose
I really appreciate
That's good.
your answers, so please
Yeah.
keep going.
Yeah, so that's basically how I implemented the prediction plus the routing algorithms. And again, thanks to Dr. Highland, we talked so much. I update this flowchart, I think at least 4 times, so.
And I don't know about the rest of you, but I want to know what those last 8 dots have, or 9 dots. Have you been watching that thing on the top? It's really cool. It's got 9 dots to go.
Yeah, but I will try to make it precise. Yeah, so the last thing, the advantage of the research stage, I get access to the data in Sacramento, and I plan to validate my routing algorithms on that. So I already had their MOD trips, like which people want to take a microtransit from where to where. And I also have general traffic demands for the whole city. So from the OD estimation, just need to reconstruct the traffic routes with these ODs plus the MOD price. So a short summary. Background, why I have this idea, start with AV to the AV data, and AV data can be useful for the MOD operators and other stakeholders. And I use that for first my prediction leads to my first research question, and then routing to my second research question. That's the whole background of a PhD topic. And a summary of my methodology, I start with simulating the data collections from distance-based sensor to the computer vision, so basically camera and the combined, so camera plus distance-based like LiDAR, radar sensors to the AV collected data. Use the AV collect data for estimation prediction will be improved in the current paper, and then use this predict the traffic states for my routing algorithm, and plus the other operation modules to simulate the movements. And for the current paper, I use two different simulation platforms, initiate a code simulation, plus my own prediction and the routing codes. And I will use the data from Sacramento for the case study. Some key findings is the idea AV can actually collect the high quality data for traffic applications. And to some extent, they can supplement the current loop detector data. Maybe in the ideal case, can substitute if we have a better traffic state prediction estimation module. And finally, for this routing application, the ideas will create a pipeline which you have vehicles running. You're running, you collect data, you predict, you reroute. So this way. And so this is again, the flow chart of the paper. And if you see all the dashed lines, means I still have to down that. I still have to finish that. That's the current progress for the routing paper. I also have the future work for the PhD topic. So starting from the methodology flowchart, the first work I can think is how to integrate with other modules, like pricing or assignment, or because you can also change assignment for a better routing algorithm, right? Or pooling, reservation, repositioning is the second part, which relevant to the routing. So how to balance like the needs of repositioning for serving future demands better and collect the data at the same time. And third thing is, again, how to create this data exchange loop for different stakeholders and for different data formats. And yeah, thank you very much. Again, thank you for all the like nice talks and the nice, not only academically, but also on the trip or travel advice here. I appreciate my time here. I would love for your comments and questions and future collaboration. Thank you so much.
Questions online? We're gonna check and see if we have a question online.
Hey, Yunfei.
Okay. Oh, Andre has a question.
Hello. This is not tied to your research, but just want to say that I'm happy to meet another cyclist.
Of course, Andre.
Yeah, I don't know how much longer you have here, but if you want some good cycling routes around here, let me know.
Yeah, I'm leaving in 1 week, but I'm really like jealous because you know, like after September, it's impossible to cycle in Europe anymore. It's cold outside. I mean, it's still possible. If you go to mountains, it's like already like icy. But here, you basically have the nice weather all year round, and you have nice route. In Germany, we can only cycle around the lake, but like, here compared to ocean, it's like
Go to Corona, they have very nice cycling.
really, really nice.
May I ask
Oh,
one question or somebody else?
Let's talk because we're left.
Oh, he left?
Well,
Well, let's.
yeah, you can read without this.
All right.
Question.
Siwa said he was sorry that he has to go, but he wanted to ask you a question on page 24 and page 26. Let's see if they're easy to do. If not, we can. On 24, he asked, even the ground truth is from the simulation data, right?
That's true.
Okay.
Yeah.
And on page 26, he asks, do we calculate the speed as network space mean speed, total VMT over total VHT?
No, that's the speed from basically the ego vehicle plus the detector.
Thanks. I'll let Siwei know to watch the video and have his questions answered.
Can you
Okay.
tell us one more time how you do calculate density from the extended floating car data?
So for like for the AVaS or
Here, how are you getting your, it's called measures of density? Or are you not measuring density directly? You're measuring speed and flow?
no, I'm measuring the density by the number of detected vehicles
Yeah,
over the lens.
over the area detected.
Yeah, yeah.
Okay, so maybe Andre was saying this, but like, that's to me in some ways obviously biased, right? Like
Yeah,
the
yeah.
vehicle itself repels other vehicles in a sense, right?
Yeah.
You don't want to be too close to that vehicle. So I assume your detection rate is not very big. And we kind of know that vehicles are not going to be right in front of you, not going to be right behind you. So you can imagine why it's kind of easily a biased estimate. Yeah. In the other direction, right, though, like if you think about it, is like an arterial network, it's going to be traffic signals. You're most likely to be in the queue compared to the link downstream where no one's at,
That's true.
right? It's not a random sample at all of the network. Whereas your kind of cars on the side of the road would be a closer way of capturing a random sample.
And another bias I didn't mention, but definitely play a big role is because we are using the data from MOD vehicles, right? And people normally take Uber to recreation or food, or like as a point of interest, right? They won't take Uber to drive back from work to home, and there will be a huge bias. That's why I think it's a dead end. We shouldn't estimate the traffic densities, but we should just observe the traffic, like see how many queues in front of the intersections, and we know, or we just we know the travel time from certain routes, certain links. So we assume like surrounding links from our traverse links can have similar patterns, and this can be beneficial for the routing.
Well, I've some thoughts about this. I think that there is some value in estimating density, maybe not so much in low density or low volume conditions, just because you know that then traffic's just a free flow, right? So there's really not much insight that's needed for routing purposes. But it would be useful if it indicates that, hey, you're closer to, if you're getting closer to capacity, then that affects your route, the reliability of your routing, right? As traffic gets closer to breakdown. So that's where I think your density estimates play a more significant role in your routing algorithm. So I wouldn't totally discount that. I think my bigger concern is if you can address that systematic bias, if in your density estimation, I suspect that it's got to do with your assumption of being the assumptions you're making as a moving observer. That if you look at if you look at your trajectory diagram, if you estimate the trajectory of your adjacent the observed vehicles, in a time space diagram, then you might be able to get a better estimate of what the true density is. By slicing it through, by slicing your observation through the space axis. So those are my thoughts. Yeah.
I agree. And also, like, I think irrelevant to the comments before regarding whether Google Maps has already done great jobs in predicting recurrent traffic patterns. I think the more interesting areas or traffic conditions I'm looking at is this congestion happening not like currently. So that will be definitely a high density scenario. And then it can be really beneficial following the way you just proposed. Yeah, I will keep that in mind. That's a good point. Thank you.
Any other questions?
Okay, so I have two questions actually. One is, if I understand correctly, you are using the MFD or NFD for routing here.
Yeah.
But then that is network wide. How do you differentiate individual routes? I mean, do you see my point here?
Yes, actually, we also have papers regarding that. We divided like network into different zones, not too small, not too big. So because if it's big, then make any sense. You will travel almost the same route. If it's too small, it's basically the same as link level estimation.
Right.
And what we're trying to do is we predict that if within a route, the vehicle will form the same path, because if you update the cluster with the same travel time factors, the different routes will have basically the same scale of travel time. But what we're trying to do is as we divide the cluster in such scale that if a congestion happening in this cluster, I can try to bypass this cluster to another cluster.
So that was you by cluster, okay, zone-based route, not really road-based. But another question actually, I'm getting to the overall idea about dynamic routing. You've already seen that for the whole journey.
Yeah.
You will have to stop and free flow traveling and so on. So I feel maybe we want to go back to the old school performance function of routing.
Can you elaborate?
I mean, how about to consider the whole average during because what I'm seeing that if it looks like you are taking average for the whole journey, then the travel speed or speed can be very different from the local speed anyway, from the traffic flow anyway. Yeah. But I think that is a kind of like an end-to-end average to me. I mean, your calculation, but then that would be almost assume like the whole period average. Then we might be able to use like a link performance function, or say your average speed actually is a whole journey average speed, already considering the demand and the congestion effect. That looks more like a link performance function to me than I'm not clear, but it's just one thought.
I think it's definitely a good point. I'm just thinking at the same time that because for MOD operations, you anyway have to give a clear routes of which link you should travel for the vehicle, right?
Right.
So how to balance this.
Or maybe this is related to the time scale. What I'm thinking is that maybe, for this routing, anyways, we're planning maybe for 30 minutes, not like 5 minutes or so, because traffic variation matters a lot when we look at like 5-minute interval. But if we're looking at 30 minutes and so on, maybe, after we average everything out.
We are still thinking of the how long the should be. Yeah.
I also want to say your first question. the benefit of the MFD, NFT, and aside from diverting around a congested cluster, is giving the customer a better estimate of when you're gonna get picked up. So even if you are following the same route, if you know that route got congested, you got a better estimate to give to the customer.
But then, how to accurate estimate this NFT or MFD definitely will be very important. But I feel this actually gets down to the definition of NFT thing. Yeah. Actually, I've done some theoretical work and then show, but this is related to stationary state. You were talking about traffic pattern.
Yeah.
What, how do we differentiate traffic pattern? Because, on the signalized network, there's got to be stop and go.
For sure.
Anyways, right?
Yeah.
But how do we define? But definitely we cannot consider stop as one pattern, go as one pattern, probably their combination, different type of combination.
Yeah.
That would give us an idea about what is like a relatively free flow, what is a saturated on the top, or even oversaturated.
Yeah.
So I feel the discussion is not there. Actually, there are gaps in the literature, but those are good observations.
That's good. Very good observation. Yeah, I don't know how to cover it now, but I would definitely keeping it on the list.
I did have a quick question about what approach did you take as far as drawing your zones? Like, how did you decide to know this is going to be your zone size, or are they different sizes, and how?
We have different methods, like so. For example, I'm very interested in their lecture 2 weeks before, because we used to use the Baroni from the detector's location to divide their clusters. And we have also other ways, including both spatial information plus traffic homogeneity. So like from the link speed density patterns to group the links, but also a lot of simulation we have done is we already have a zoning system from the research project, which based on the administrative district. So I can't say, okay, we used a certain way to do it, but like we use it different ways, but based on spatial information, traffic patterns, and their administrative perspective as well.
Okay, so if you wanted to recreate this in a different area, there would have to be some work done creating some. It's not.
Yeah.
All right,
Wow.
great seminar. Thank you. It's the audience, that was great.
Yeah.
Could advertise, right?
Oh, yeah, also in the afternoon, we have, Professor Ketan Satla from USC. He's going to present in the CE seminar. I believe all of you got an announcement, right?
Yeah.
I look forward to seeing you all over there. Yeah.
Sorry, what was that?
From 3 to 4 o'clock.
Today?
Yeah, today,
Okay.
the CE seminar.
Oh, okay.